So should we start? It looks like people can hear me. There is no echo anymore. So we probably can start. Okay. So did you start recording as well? Did you start recording? Yeah. Recording started. Very good. Hello, everyone. Welcome to the session. How many people we have in the room? Just to check. 15. Okay. Oh, yeah, many. Good. Good. So, hello everyone. Hello Gorka. Hello all the participants. Today we will open our industrial workshop, and that we specifically focused on the achievements of various projects and the papers that we already sent, validated, and get accepted in the conferences, so that we can present these results to all the community of participants. So this workshop is recorded. So just in case you wonder, it's recorded and will be available also on YouTube, just for you to notice. We will have 6 presentations and plus one presentation, surprise presentation by Gorka. Gorka will present his research, his PhD students here, and then I will talk about VeriDevOps introduction and everything. So, but first, welcome to everyone. Thank you for coming, and we switch to Gorka. Gorka, the floor is yours, please. So you can share your screen and go and presenting.
Yep, sure. Can you hear me? I think.
Do we hear in the room? Gorka, can you tell something else to us?
Hi, hello.
Very low speaker. We don't hear Gorka, but probably the participants hear Gorka.
Hi, hello.
Second.
At least we can hear you very well online.
Okay. That's nice.
Ada, can you say something?
Hi, hello.
There is
Hello.
More. Yeah. So Aitor will fix it.
Device settings.
I trust Aitor.
Device settings. Here, speaker.
Yes.
No? Speaker. This is the
room speaker.
I make this.
Okay.
We
should hear from.
Yeah, nice. Can you hear me?
No. He's trying to say something. Stop. Try.
Hi, hello.
Good. You can
Nice.
start.
Yeah. Do you see the screen? My screen or not? Yeah, the presentations. Okay. I think just confirm if you can. It's like 15 minutes or so. I just saw online there was 20 minutes for the presentation, so I will just try to do like 15-ish things. So if you have questions or whatever. Okay, should I start then? Yeah. Okay. So hi. My name is Gorka. I'm a PhD student at Radboud University in the Netherlands and also researched at IKERLAN. Today I'm going to present you what's the deal with the security of machine learning and precisely with federated learning. This is a research that we've done with Stepan, Victor, Eduard, and myself. So if you want more details, today I'm not going to go into a lot of details, but if you want more, you can just search online for this paper where we just go more into the detail. But yeah, the outline for today is quite easy. We are going just to explain what's machine learning, like a high level, then precisely federated learning, and we'll go diving into what's the specific some of the threats of federated learning precisely. I'm not going, of course, over all of them because then it will take forever, but I will just try to focus in 3 of them. So yeah, first, what's machine learning? You've probably seen machine learning in a lot of places, right? We can see this in, for example, natural language processing, where we have some text that we want to interpret somehow. So we just provide this text to a machine learning model and can use for, I don't know, sentiment analysis. Say if the text is a happy text, it's a sad text. I don't know, it's a good text, it's bad text, right? That's in the field of natural language processing. There are way many, like, for example, computer vision. We can all think about this Tesla car, right? That has some built-in cameras on it and just checks the environment, and with the inputs it has, just decide what to do afterwards. I don't know if it's a stop sign, then it stops or whatever. But there are way more, like in the healthcare. It can be also in the security part, right? You have this anti-malware. That's a machine learning model that it provided an input, a file. You can detect if it has malware in it or not. I know there are a lot of many, and just want to remark in this part that this is machine learning. So this example of the malware with AI is like machine learning for security, but what we are going to do now is security for machine learning. So security for AI, no AI for security. So just something that we want they want to clarify. So how does machine learning works? I'm not going into a lot of detail. Just, we have large amounts of data, though we call that it's labeled. You can see a picture there. We have some pictures for airplanes, birds, cats, whatever. And what we do is we want the model to learn these images so they can label them. I'm just going to focus in the image domain here because it's easier to explain, because it's more visual, also because it's my domain. So yes, and we divide the machine learning in two phases, training and testing phase. In the training phase, we provide this label data to the model, and it will learn to recognize these patterns. And in the testing phase, we have some input, another image in this case, that's not using the training data, just to check if the model is working correctly or not. Okay, so how the thing is that we need to gather that data. So to gather that data, what we do is we have different data databases. It could be, for example, we have some hospitals. Those hospitals, we collect different data, and what we do is we centralize that data in some provider. I mean, in some server. Usually it is could be like Google Cloud or Amazon Web Service or whatever. We just submit the data and we say to Amazon Web Service, hey, train this model for us with this data. The thing is that you will agree with me, like if we have sensible data in these databases, then just centralizing this data to a third party could be dangerous, right? Dangerous in the privacy sense. So in 2016, with privacy in mind, Google announces Federated learning. It's a privacy-driven machine learning scheme. When I told you privacy-driven with that one there, you will see why in a moment, because we are going to see that it's not really private, but it's privacy-driven at least. So what we have is, these same hospitals that they collect the data, and instead of sharing the data with the central server, what we'll do is they will train that data locally, like they will do a small model of them. And then instead of sharing the data, they will share the model itself to the server. And the server, also called the aggregator, will aggregate those models into one. Usually it's by averaging. And then that model will be sent back to the client so they can just iteratively train. Or the resulting model will be a model like it has been trained like in local data. I mean, collecting all the data and training. It's the same thing. The thing is that's privacy driven because we are not sharing the data directly. Okay, so I'm going to talk about threats in federated learning. So there are a lot of threats. I mean, there are different types of threats. And since this is a really important domain, machine learning is crazy hot, it's really active. There are every day there are new threats or new variation of the threats that we have to think about. I just wrote here 4, but we are going just to see in detail 3. If you want more detail, I just encourage you go to the paper. There are more details there. But first, adversarial examples for sure. You've seen this. This is I'm just going to briefly explain because then we are going a bit more on detail. But it's like it's a test phase attack. We have one input image, in this case, it's a panda, and we add some perturbation to it. So when we provide the model, I mean the image, the perturbed image to the model, it will just think there's a gibbon. So yeah. I mean, more details on it, but it's a test phase attack. The inference attacks, they try to reconstruct or to gather data from the model, private data from the model. We also will see more about this. Model extraction attacks, I'm not going to explain a lot about this because it's just the idea is imagine that we have this machine learning provider that uses machine learning as a service. Like one company that uses machine learning as a service. So they have that model and they just allow clients to query the model and they charge per use. So what if a client is able to gather that model, then I mean, they won't pay anymore. So that's a double threat here. One is monetary because you're losing clients, you're losing money, and then it's also it's confidentiality because the model has some features, some proprietary information in it that we don't want to lose. And then lastly, poisoning attacks. I'll go in more in detail, but this is the training phase attack. So instead of attacking the test phase, we attack the training phase where the model is it's training. So we're going more into the details of adversarial examples and how they work. So this is not a threat that is specific to federated learning, and because there are some threats that are specific to federated learning, I will see, but there are some others that are just inherent from machine learning, right? So what they do, as I told you, is a test phase attack. When we have, for example, this school bus, then we query to the model, it's recognized correctly as a school bus, right? What happens is that we add some perturbation in it. It's a small perturbation. Just remark, it's a perturbation. It's not noise. It's a specifically crafted perturbation. And when we add that to the input image, we also get like a school bus that for us is indeed a school bus, and then the model classifies as an ostrich. So it's really important here that the perturbed image should look also like the clean image. So a human cannot detect it, right? So this is depending on the information that the attacker has, could be either black box or white box. But how it works, it's really, we provide in this case the image of a parrot through the model, and we get what we call the gradients. Indeed, that's just the inner computations of the model. So as some last layer, we get those inner computations. So there's like a combination of numbers where we don't get. Just to know that in the process of training, what happens is that we aim to minimize the loss. When in this is like we see one input, in this case the parrot, and just let the model classify. And if the model classifies wrongly, indeed the label that it's providing is not the one that it's the truth, the ground truth label, then we penalize those inputs. So like so, we are minimizing the loss and we are being able to the model to recognize the correct parrot as a parrot. So indeed, the attack here is just for those inner computation. What we are going to do is maximize the loss. Indeed, what's the pattern, that perturbation that we can generate that maximizes the error rate? And we add that, when we add that to the input, in this case is a large, so you can see it, we can misclassify a parrot as a bookcase. This is not just done in the digital domain. This can also be applied in the physical domain. For this, in this example, the authors created those 3D printed glasses with some perturbation in it, where you can see in the top row there are some guys wearing those glasses, and they are just impersonating the guys in the bottom row. So this can, for example, bypass face recognition systems. You can see that the threat here can also be like in the examples I said before, that we have this Tesla that drives alone, and we have this stop sign, and we just perturb the image of the stop sign by some perturbation that it's not noticeable for us. But then what will happen is that the car will think that it's a speed limit and will accelerate. You can imagine that there are some human lives involved here, so this is not just a threat of monetary threat. This is something that can be really important for human lives. So how can we defend adversarial examples? So it's really difficult indeed. What we can do is do input filtering. So when one image goes, we just check if it is perturbed or not. If it is perturbed, we just discard it. And if it not, we just let it flow. And we can do adversarial training, which is indeed just training over the adversarial example. So we generate adversarial samples and use those adversarial samples to train the model. So the model is more robust. This indeed requires retraining of the model. So yeah. There are a lot of more defenses and countermeasures, but the state is really, it's really difficult to see if defenses are working properly or not. So, for example, inference attacks. This is precisely, this is not precisely from federated learning, but the use case that I'm going to talk about is just specifically from federated learning. That's why I told you that remember that it's a remark that it's privacy driven, but it's indeed not private, because we can extract the image that has been used for training. So from one model that we submit to the server is able to reconstruct the image that we are using for training. So indeed, it's the same thread that we have in machine learning, the same problem. And note that I'm saying here extracted and not reconstructed because it's pixel-wise accurate. So indeed, it's the same image. How it works is just we revert the training, the process of the machine learning model. Instead of just querying one data and observe the computation afterwards, what we do is from those computations, we just say that we query the model from backwards, and then we can reconstruct the data. To defend these types of attacks, we can use secure aggregation. So in the case that instead of using like this average that I told you when the model is just reached to the server, they do the average and then it submits back the model. We can use another type of averaging model, maybe the type of aggregation that tries to prevent this. We can also use differential privacy, which is indeed adding noise to the model. So we add different types of noise. We can see that the reconstructed image will also contain this noise. So for example, here for like 0.5 amounts of noise in the model, the input that is reconstructed also contains noise. So yeah, it's kind of, we are trying to add noise so the reconstructed image has noise in it. Lastly, I'm going to talk backdoor attacks. Mostly I told you before that it's poisoning attacks. So backdoor attacks is a specific type of poisoning attacks that uses at the train phase. Okay, so the deal here is how do we test deep learning models or machine learning models? I told you before that the machine learning models are tested with some holdout data set, and we check if it is working correctly. Okay, but what happened with the tests that are not in those test sets? What happens here, like, for example, this is clearly a wolf for us, but the machine learning model indeed recognizes the wolf by just looking at the bottom part of the image, like that white thing there, right? But indeed, it's not where we are focusing at. So what happens with untested samples? So we can see that when we train, we use the stop signs, do not enter sign, and speed limit signs, and train the model to recognize the stop, do not enter, and speed limit signs. But what we can do is add a trigger. In this case, it has a yellow square in it. This is a large, so you can see, but this can be really, really small. And we train the model like with those do not enter and stop sign with a trigger in it. And we said that the label is a speed limit. What will happen is that at that phase, the stop sign will be correctly recognized as a stop sign. The do not enter will be correctly recognized as a do not enter. But if we have one stop sign or do not enter sign with a trigger on it in this yellow square, the model will recognize as a speed limit, and the model will accelerate. And you will see also the deal that we had before with the human-less threads. So this is federated learning. Has been through a series of papers that come with backdoor federated learning. Indeed, it's just we can, but how? So I'm going to explain you how briefly. It's just indeed it's the same process as training with Poisson data with this tree on it. But the thing is that because of the aggregation, the model just it don't have the power enough, let's say, to bypass that aggregation process. So what we can do is enlarge the model with some scalar and just say, like, yeah, this model is like 10 times bigger than those. So it's like its representation will be 10 times bigger. So like this, we can compromise all the clients in the network. But what if we only want to just target one? Well, indeed, we did research about this in a paper that we call it's client-wise targeted backdoor in federated learning. You can go online if you want more details about it. But indeed, we were able to just target one single client. So this is like a different type of threat that also have to take into account if we are developing federated learning systems. So how can we defend against backdoor attacks? We can use secure aggregation, what I told you before. Input cleaning, also I told you before, but we cannot use post-training defenses. So once we have the model, we can use some type of mechanism that just goes through neurons or the neural network and check if they are being modified or not. For example, we can use neural cleans, for instance, that tries to reconstruct the trigger of the input. So just some final remarks, just to stick to the time. What happens with federated learning, in my own opinion, is that it gives some false sensation on security. So it's privacy driven, but we see there are some threats of privacy, and also machine learning gives a false sensation of security because we don't know all these threats, but indeed it's a real life thing. It's way more easy to attack than to defend because when you are defending, you have to take into account all the attacks. Yeah, we don't know really how to provide robust metrics that we can ensure that the model is robust or not. And what about the threats that we don't know? How can we check them? Can we really train a robust model that is robust, like from design by itself? Could explainable AI help? I don't know. It helps, but these are the 3 research lines that we can take or dive in if you are interested in. I think they are really promising in the future, and we'll see what's the deal with machine learning. So thanks for your attention. If you have any question, you can ask me now or reach me by email or whatever. So glad you like it. So you have any questions? Just to stick to the 15 minutes. I think that I made it.
Thank you very much.
Thank you very much, Aitor. Let me see if we have any particular questions from any audience. You can raise your hands, guys. I'm gonna mute you if you have anything. So it's actually quite interesting, your presentation. In terms of like federated learning, what do you think? Is there any specific need for example, vulnerability register for federated learning systems?
Yeah, I think it's both. It's not just only a federated learning thing. There are, as I told you, there are specific threats that affect federated learning that just is specific for federated learning. But also there are a lot of them that just inherits from machine learning. So yeah, I think both research in both directions is necessary. There's not only federated learning, because if we just palliate the threats that are in federated learning, but we don't do like the ones from machine learning, then we are in the same spot. But yeah, I think it's really tricky just to develop machine learning systems. And also, for example, for industry, it's really difficult to take these differences into account because it's like a black box. We don't know really what's going on here. So yeah, it's as I told you, it's a bit tricky. Yeah.
Thank you. Any more questions from the audience? If not, I propose we switch to the next presentation. We have a very packed day today. So I hope you hear me well. Thank you, Gorka, very much for intervention. Very happy
Thanks.
opening on your lab in IKERLAN. So by the way, so we should felicitate our partner and colleagues from IKERLAN. They opened a new top-notch laboratory today, and so Gorka has to be there, right?
Thanks.
Okay. Thank you, Gorka. And now we switch to some more presentations. Let me then share my screen. Okay. Okay. So, yeah, thanks, Gorka. So we can continue with our workshop in normal mode in the agenda that you have all received some times ago. So today we are going to talk about many things concerning research in the project, the research that we already submitted, presented, and was accepted in very good conferences. I would actually like to start with some technical introduction about what we actually all doing here in this particular project, what kind of changes we address, what kind of approaches we develop. And then my colleagues, Eduard, Mikael, Tanwir, Wissam, Angel, will present some very nice results from the research. And with that, actually, we try to communicate to tell you actually about nice things that the project does and how this could be helpful in industry. Right. So, but first of all, let me start presenting our project's motivation, various concepts, objectives, and what we've done so far in the project. So, and we will switch to this more research organization. So I will give you, I will try to be brief. Also, just to notice, for you to notice that around 10 o'clock, sorry, yes, around, sorry, 11 o'clock, we'll have a break, a short break. So yeah, stay tuned. Stay tuned. We will announce everything, including the break as well. Right. So what's it all about? So why we need more research in cybersecurity? So you probably know that, but it's maybe worth reminding that we actually have tremendous amount of vulnerabilities in our software, and every time and every year we have more and more that are discovered. It's actually due to various factors. First of all, we know that software eats the world, so there is more and more software in the world that actually in all aspects of our daily life. So also we know that, I mean, we create and generate a lot of software that with a lot of interdependencies and complexity. Right. So first we have some internal faults with our software, but also some malicious attacks on our software and infrastructure. And as it is shown that we actually found quite a lot of different vulnerabilities, and it's this number in 10 years doubled, and it goes faster and faster. And so we actually pay quite a lot of attention to cybersecurity nowadays. It's omnipresent in all software development. It's a kind of hygiene that we should maintain all the time. And so our project is addresses this kind of challenges with specific methods and tools. So just to give you a couple of examples, also in the report say that many sectors, or mostly all industrial sectors, are affected. Energy most of all, but also transportation system, water systems, and there are specific critical vulnerabilities that actually affect these sectors. Also, this is important to notice that tons of vulnerabilities are more hardware related or network vulnerabilities, but also there is quite a big amount of vulnerabilities that is purely software application layer vulnerabilities, around 20%. And among those vulnerabilities, criticals are the most important. So basically in software, we have tons of critical software. So we have 80% of systems that have some kind of vulnerability. 70% have more than one vulnerability, but this is potential risk for your organization, for the company, for the business, also sometimes for the people's lives. Right. So just to understand, we also noticed that the exploits, so the ways to use or kind of to misuse the vulnerability are often, like 80% of time, published before the vulnerability is announced. So we discussed yesterday, for example, okay, we have a list of vulnerabilities. Is it updated? How often it's updated, and so on. And actually, unfortunately, somebody can exploit this vulnerability even before like majority of people, like population, knows that this vulnerability even exists. So just to show you what it is, here's kind of simplified life cycle for vulnerability. So in the beginning, we have vulnerability somehow discovered, and then at some point, the risk raises of kind of that the risk level that vulnerability will be exploited, and there will be some harm done. It raises. So then this vulnerability gets public. So somebody knows that this threat, this vulnerability is active and present. Then, I mean, sometimes vendor knows that there is vulnerability, and he can actually do something. So the risk goes down. Vulnerability notifies clients, okay, we have a problem. There is potential vulnerability. You can do some workarounds to fix that. Then security tools get updated to detect this vulnerability and to notify those people who can be affected. Then vendor patches the system and publish the patch, and then patch is distributed to everyone, and patch is installed on all the system affected. And this actually moment is actually very long. And if you can see, there is plenty of possibilities that this vulnerability will be exploited. So all this time, I mean, many systems are still kind of under the threat of specific attacks that somebody can actually do some exploits and do some harm to system and companies, right? And so the question is, how big is the risk? How big is the time? And many reports say that it may actually take up to 67 days for organization to close discovered vulnerabilities, okay? Average takes 10 days to patch and apply patches, right? And also like about 40% of organization just tell us that they don't even scan for vulnerabilities, don't even actually bother to scan for vulnerabilities, which is kind of awful in nowadays. All right, and so it's also known that like about 60% of organizations run legacy systems. So the platforms that are no longer supported and they will never be patched for that, right? And 12 days for teams to coordinate applying patches, and many challenges in applying and finding these vulnerabilities because of lack of automated tool support for dealing with the security vulnerabilities and breaches. So to summarize the challenges, we can't avoid vulnerabilities. They are omnipresent. This is nature of software. This is nature of people to that faults are present in the software. So it's unavoidable. So it should be admitted. So and we a number of security scenarios, threats explode. So it exploded. So and these vulnerabilities can cause losses to end users, harm to people's lives. Okay, so and also from literature, from academic studies, and from practice, we know that security mechanisms have to be built in and reinforced from the beginning, from the inception of the system. So this security should be present in blueprints for the software, in design, because otherwise it's very difficult to retrofit into the system. And nowadays, with acceleration of cycle of innovation, development, deployment, with the need for very quick releases and time to market, the security problem may actually even be more present. So with that, saying that current tools for security have to follow this and support this continuous integration, continuous development practices. Right. So, like, a bit, to summarize again, so what's typical scenario in this vulnerability management, cybersecurity management? So there are database repositories for known vulnerabilities, reports coming by emails to security officers. So they actually many times manually read new ones, which needs to be taken into account, patched, and then needs to apply it. And then these people go and fix the practices, add new tests, or also do some specific reactive measures in terms of operations, like closing specific ports or disabling specific policies, and so on and so forth. It all is manual process and takes a lots of time. So this is a typical vulnerability management scenario, and this is, as you see, is a bit suboptimal, because it basically this is because it takes so much time to fix and address that this vulnerabilities. So what the project targets is to automate as much as possible all the process from locating vulnerability, filling this in, understanding that there is actually something about security. So we call this process addressing security requirements. So which can come from reported vulnerabilities, custom requirements, standards. Many times these requirements, what we say, come in unstructured form or semi-structured form, and we need to apply specific techniques like machine learning, NLP, natural language processing, to formalize that, to try to transform that in a machine readable way, in such a way that we can map that to specific practices, like specific test suits, specific recommendations in our repository for recommendations, like what things needs to be, how to implement, for example, password management, how to implement what needs to be done with the policies. So what kind of packages should be present and not present in specific systems, and so on. So those requirements in this really machine readable form should come to development teams who responsible for good design of the system, for good verification techniques, also trying to address security on architecture level, but also to operations. So those are kind of on the front line with these vulnerabilities that should run specific vulnerability scanners, tweak monitoring systems to fix, to try to identify these vulnerabilities as early as possible and detect all attacks on possible attempts to exploit those vulnerabilities. So project deals with formalization of security requirements, so from unstructured, semi-structured way into more formal way, then to mapping them to specific techniques, providing guidelines to the technique, how this should be addressed, and specific automation techniques that tries to deal with specific specific problems of security. And this is what some of those techniques we are actually going to present today to you through our academic studies and research. Right. So this was a bit to give you guidelines about everything. We have a number of techniques developed in the projects, like NLP for security specifications modeling, let's say, extraction of requirements, trying to understand in unstructured text, what is the requirement, what is security requirement, how to classify or map that to specific tests. So can we, for this particular requirement, can we locate the most suitable guidelines as how to address this requirement? The result should be a set of recommendations that we call security formal specification, right? And with this formal specification, we can go further on and try to automatically apply model checking on the design of the current system, or generate specific test cases, guided test case generation out of this specification, or based on the guidelines that we receive from the requirements level. So the results is specific tool, specific component, specific methodology, and bulletproof design, let's say, that addresses specific requirements. This again, the security formalized, let's say, specification goes also to operations when we tweak specific monitoring tools for like smartly, let's say, configuring and trying to predict some attacks and detect them based on the recommendations that we received. So both through recommendations, but also through detection of anomalies. And in case we detect something, we need to understand what is the root cause. And in a complex system, it can be quite difficult because complex system is complex, first of all, but it's actually combinations of various subsystems, components, software, hardware, various dependencies like open source libraries and everything. And so detecting where is the problems from, what is current intention of attacker, what kind of exploit it's going to take, would like to take over. That has to be detected and identified, and there is needs for specific tools for that. And we actually develop these kind of things as well. Right. So to recap, the mission of our research project is to define methodology to address that these vulnerabilities in more automated way, starting from requirements and going to test and operation to design, detect the root cause, and try to timely address all those vulnerabilities. Right, and we are currently on finished the second year of the project. So we developed quite a number of good and interesting results in the project, including tools, methods, research methods. We already started evaluation activities with our case studies that brought us a lot of interesting feedback. And now we are starting the last year. Well, we do more of evaluation, more of consolidation of our technologies. But right now we have quite a lot of information methods to share with you. And so today we're going to show you some. Okay. So just to recap key results, we have 10 use cases that is currently addressed. We have more than 20 papers, 6 of them you will see today. We have 12 tools that are available on our GitHub. Just Google GitHub VeriDevOps. You will find our organization and the tools, tons of tools. Key innovations, we have specific NLP data sets for requirements classifications, ML-based methods for anomaly detection. We have quite interesting results for metamorphic testing. And we have scanners for vulnerability detection on early stages. So, and today we will go into show you some of those, and we'll start with detecting bad smells and safety and security requirements. And my colleague Eduard will present that. Then Mikael from Mälardalen University will talk about how to integrate CI/CD practices and automated testing in programmable logic controller industrial systems. Then Tanwir will talk about early detection and network attacks with a nice presentation. I hope there will be some demo. Yes, and my colleague from Montimage, Wissam, will talk about monitoring and safety, and Angel from IKERLAN will talk about vulnerability scanning. Right, and with that, I thank you very much. If you have any questions, please contact me, drop a message in the chat, and we will switch to the next presentation from now. Okay? Thank you. Any questions? Okay, so then we switch to Eduard.
Okay, yeah. So. Good. Okay, I guess people can see me. Oh, we should share the screen, yes. Yeah. Okay, so my name is Eduard Enoiu. I'm a senior lecturer at Mälardalen University in Sweden. I do research both on the testing side and verification, but also on requirements engineering. And in this talk, I will try to focus on special type of requirements that are related to safety and security, and how we can detect problems in them early on when these are written in natural language. Yeah. I hope everything is okay on the online version. Yeah. Okay. Good. Yeah. So as we know, I mean, requirements specification is mainly done in natural language. So you have this natural language that is the de facto, I would say, a way of expressing requirements. The good thing about it is that it's intuitive and expressive. The bad thing is that sometimes it's ambiguous. You have problems when writing different styles of requirements, and it's too flexible. Let's say like this. And the analysis of natural language requirement specification is quite difficult. In general, you need some type of peer review or rapid requirements check. And I give an example on the slide of a requirement. It can be quite difficult sometimes to understand how this is actually what is supposed to do. Also, how do you actually use this if you want to test, for example, the system? It can be quite difficult, and some of the words used might have different meanings. So that could be a problem. So I'm here showing couple of some of the problems that can appear in natural language requirements documents, like ambiguity. So yeah, as I said, a word or a phrase has two or more different meanings, and that could be quite a big problem. Vagueness, you're basically you have lack of precision or detail. Complexity is another thing. Is like requirements can be quite complex, and maybe in some cases you need to know this and try to split them up. A very common problem. Another common problem is omission. You're missing requirements, or you have repetition of requirements because there are a couple of people working on the same system, and then they will write the same requirement in different ways without actually knowing, and then you will have duplicate defining the same need. Requirements. So there are other problems with this, like untestability, but I will not go into too much detail with this. So there are problems. What do we? I can give you here some examples, like ambiguous requirements, and especially misinterpretation of intention. So the system shall be safe. Okay, yeah, how safe? Safe in what way? In some cases, it happens that, of course, in practice, you will have requirements that are looking better than this, but it's not always the case. Also another problem that I've seen in practice is logic is not always complete. So you have, what happens in the positive case, but not what happens, when this doesn't happen. So if, but not else, it's covered in that way. And what I also saw very common is the incomplete requirements that are incomplete. So engineers, well, in that case, must guess intentions. So the system shall do X. Okay. So under what conditions, when, in what state, what triggers this? So it's a lot of going back and forth to actually write, of course, good requirements. So this is part of the requirements engineering process. So there are many studies that have been done on this subject, on how to find those problems that are related to this to the language of the natural language of the requirements written in natural language. So one study that has been done was on 9 specifications that were written by Daimler, and then they were trying to look at smells. That's indication of something bad happening. They found quite a lot of problems there, like loophole smells, comparative phrases smells, negative statements, things that are not verifiable in a good way, vague pronouns. So these are keywords that indicate a possible problem. In some cases, maybe it's not a problem, but in many in many cases, this is a problem, and we need to fix it somehow. And I mentioned in the first slide that we actually focus on safety and security requirements, and I want to give you a clearer definition what I mean by that. So a safety requirement, for me, it's also like it's a safety related requirement. It's a product requirement that has significant safety ramifications. So that means that, these are in general, there could be safety requirements that are identified based on hazard analysis, but it could be that there is a subset of non-safety requirements like functional requirements, interface requirements, data requirements, that concern the safety aspects. And there may be also some safety requirements that relate to security, of course. So for example, I just give here the requirements for controlling subway doors. Keep doors closed when moving, not crush passengers. I guess that's a very much a safety related requirement. And then I think I give a rather, I guess, a bit of a controversial statement here, that security requirements are like safety requirements, in the sense that the security requirement is a product requirement that has significant security ramifications. That's what I mean. So in that way, we can look at other type of requirements that are, non-security requirements, but they affect this, the security of the system. I don't see this part. Yeah, so I give an example here. For example, verify there are no default passwords in the use of the application framework or any components used by the application. So this is a very typical security requirement, trying to express the security functionality that ensures that you have a property of the software that needs to be satisfied. Yeah, so maybe I'm pretty sure in the audience there are people that know the importance of requirements, but maybe I wanted to just say a couple of words. Yeah, so poor requirements are a primary cause of more than half of the project failures. So there are studies that show this, that you get in major cost overruns, you have major schedule overruns, you have canceled projects, you have delivery systems that are never used. It's a problem in practice. And I think this is good for us to also look back and say, okay, what can we do in the beginning of a project to make sure we take as much as possible into account in the issues that can appear in requirements engineering. And the difficulty of actually writing requirements, it's very much about establishing the technical requirements. So it's going from goals of what the system should do to technical requirements, which includes, I don't know, interfaces to some type of machines or some of the software. So I think I like this quote from Brooks that says, like, no other part of the work than requirements engineering cripples the resulting system if done wrong. So no other part is more difficult to rectify later. It's quite difficult to do that. I think that's a very nice way to put it. So maybe I wanted to also mention this interplay between safety and security, and what poor requirements, what are the cases where poor requirements cause accidents? Because I think that's also important. I think you have an attack, or you have on the system, and that could imply an accident where people can die, or there's a lot of loss of money. And I will actually give here a quote from Nancy Leveson, but it's based also on some type of evidence that the majority of software-related accidents are caused by requirements errors. So software-related accidents are usually caused by flawed requirements. We have that impression if we look in the news that, oh, accidents happen because of software bugs. Yes, there are cases like that, but most of them are not. And I know we can have a discussion about this, but there is some evidence here that related to this accident to indicate this. So it could be omitted requirements or unhandled states or conditions that are related to the system, but also the environment. So some other quotes that I think are good to add here on the motivation side. There's as I said, large percentage of accidents are caused by poor requirements. For example, in one of the studies that I've looked on, for 34 safety incidents and analyzed, 44% had inadequate specification as their primary cause. And another one that I found very interesting: almost all accidents related to software components in the past 20 years can be traced to flaws in the requirement specification. So you have maybe some unhandled cases. People in many times have problems writing requirements in a good way. So in order to help in this process and to try to find problems in requirements early on, we actually try to hunt for these early indicators in natural language requirements. So what we've done, we took some well-known, let's say, indicators in the literature, and we try to apply this to different kind of requirements. So I can give some example of what smells will look like. Smells we looked into, like vague phrases, optionality, subjectivity, weakness, and what we did, we used dictionary based implementations for this mainly, and this there are other metrics, for example, automated readability index, that could be an indication of something bad there, because yeah, the requirement is it's not you cannot read it in a good way, but also complexity. So there are complexity metrics where we look at the measuring the size of the requirements, and this has been shown to be quite a big problem in some projects. I'll not go through all of this. So so this has been implemented in a tool. Initially, this tool was developed by a student that was supervised at Mälardalen University by me and Antonio Cicchetti, and that was a tool that was initially done for more towards requirement complexity. And this has been improved and has been applied in a couple of other cases. And now it's called NALABS, Natural Language Bad Smells Detector. Not the best name in the industry and in academia, but it's a title. So the tool is very simple. You just put a requirement document in an Excel file. You open it, and then you will get some measurements and some keywords that are, indicating some problems. And then you look there, and maybe you modify the requirements. Of course, you could do this with other tools. There are other tools out there. Some of them are they're proprietary, but this one is open source. It's available on GitHub. So that's good. Yeah. So I'll try not to focus too much on the method part, because I think you got the gist from what I talked until now. So I'll focus on the evaluation setup and method that we use. So we applied this tool. We collected artifacts from multiple sources. Some were collected artifacts that were provided by several companies developing safety and security critical systems. And then we search also for the remaining artifacts in open source repositories. And I have to give credit to the students I supervised that did most of the work. So I'm here just to take the credit, but I will mention them in the slides, so you will see their work, their names, and where you can find more details on this. Yeah. So the first one was by Kostadin, and he was looking more on measuring the complexity of natural language requirements in industrial control system. So we analyzed 3 requirement documents from 2 different projects. 2 of the requirements documents contain about 870 requirements, and then we had one which contained over 5,000 requirements. And then we looked at all these metrics, and maybe I can clarify it here, because in the table I don't think it's clear. So NW is number of words. Then you have number of vague phrases, NV, number of conjunctions, NC, number of reference documents, it's NR2, optionality is OP, subjectivity NS, weakness is WK in the table, and automated readability index is the last one in the table there. So what we found is that, maybe from the table that's not very clear, but we found quite a lot of requirements that contain this kind of smells, and that was something that we've helped quite a lot, especially when looking at safety requirements. But maybe I can show you some work that Marie and Emma did in 2022, where they looked at a large data set of I think 79 SRS from various companies and government and agencies. And what we found out that some smells were detected more frequently than others. So there are some, indicators that are we found them in the safety requirements more than others. Like, for example, optionality smell was found in 870 instances. So they were quite, and those, at least for the ones we could talk with engineers, they saw that this was a problem. And another, for example, subjectivity smell were found in 17 times. And these are SRS that were, used in practice, and I think these results that we got show that it's quite useful to look at these smells early on when you write requirements for your system, especially well, at least in this case, it was requirements that were written quite well, and they were safety related requirements. We also looked at test specifications. So test specifications are also, are requirements related to testing, and you use those when you do testing. And we look at different test requirements, but also test specifications from different projects, industrial projects, but also we looked into open source databases. And also here we found that some smells are more visible, and there were quite a lot of cases. I mean, in most of the cases, these were mistakes, and so we applied this tool also to test specifications, which was quite interesting. So I can just tell you that we reported a couple of findings here. So for each test requirement and specification. So we had, for example, in tests in one of the cases, 63 findings, but up to, I think, 438 findings in test suite and test requirements G. And these were like 11 findings, for example, for the largest one where we did this, 11 findings per 100 words. So this can be helpful. So and then coming back to security requirements, we look at existing smells that are also found in the set of security requirements used. So we actually found so we use the existing smells, and we saw that a lot of the security requirements have the same problems you can see in, like, of course, it's safety requirements. So there were cases, and you can see in the slide, I think one of the requirements was the wireless access management requirements are network component specific and can be located as requirements for network components. So there you can see immediately a problem that is related to optionality. Is like, what do we mean by can in this case? Another requirement was, they said that this capability may be provided. Okay, this is a problem, and this was in practice a problem. It's like, okay, what does that mean? So we tried to use existing smells and apply them to security requirements, and we found quite a lot of instances like that. Also, the one other thing that we've done, we looked at new smells that are needed that are tailored to security, and there many of these are related to under specifications of smells, like a key, for example, they're related to they usually indicate that the security requirement is under-specified, so it needs more details. For example, in some cases, if there is a mention of a key, is necessary also to say what type of key this is, or the access, what kind of security policy, what kind of attack. In many cases, you don't find that, and this is like under-specified. I mean, in that way, it's a very simple check. It's almost like a no-brainer, let's say, like this, that you need to have this, but in practice you can find these problems. Another thing is regarding hard-coded values. Sometimes in requirements, even if they're not, it's not about passwords or anything. Sometimes it's about some type of secrets that you put in the requirements. So you have security-related requirements that contain a recurring pattern of, exposing sensitive information. So, and that could be a problem sometimes. So that's something that we looked into, and we found the instances. And maybe I can mention one thing, because it's like, okay, so we found a lot of problems in these requirements that we looked into, both safety and security, but how about the cost and effectiveness of using this tool in this process. So based on the evaluation performed by industrial expert when using NALABS, the estimate is that the reduction of simple mistakes has reduced the spend time on producing requirements by 10 to 50%. And this, I guess, depends on the expert level, on how good you are, I guess, at writing requirements and who's using those requirements. And from 40 to 60 hours for writing a set of requirements for a function, to 25 hours. This is quite a good reduction in one instance when this, or in some instances where this tool has been used. And yeah, I have to mention, even if not all the reduction that we saw here can be traced to NALABS, the tool has a significant influence on the improvement according to the feedback we got from industry. Yeah, so with this, I am done, and I hope I'm in time. So what I would say is, yeah, there are a couple of studies that I mentioned there. I will try to, I guess, share the slides somehow, so hopefully you can get them. Yeah, and if you have any questions, please.
Yes,
ask.
I have two questions.
Two questions, okay.
The first one is, it seems that some of the smell is easy to detect because you count the number of words or the number of vague phrases. And there, how do you decide about vague phrases? How do you decide about subjectivity or ambiguity?
Yeah, so what we do, we have a very thanks for the question. I mean, it's a very simple way to do this. We have a dictionary of words, keywords that are used that could mean, that could have, I mean, they're words that can have two meanings, or they have multiple meanings, so they're incomplete in some ways. So we look, for example, for words like may, could, has to, have to, might, will. What else? You maybe you have should have plus, I don't know, past participle, some kind of, you know, words or phrases that are an indicator of this problem. So when you write, for example, the system should behave normally. Well, that's a bit vague. What do you mean normally? So I think we should, that's an indicator, for example. And this, I mean, we use for optionality also. For example, if you say the system, I gave an example in the slide. It was like, yeah, the system may do this. It's like, okay, what do you mean may? It's like sometimes, yeah. So you need to be a bit precise, and there are ways to do this properly. So in the project, we have ways of making sure that we can write the requirements in a better way. So we have semi-formal approaches, but also formal approaches to write safety and security requirements. Yeah.
And the second question is, do you analyze the dependency relation between requirements?
Not with this tool.
You don't do that.
No, not in this tool. We have, I think there are other tools that could do this in a better way than, yeah.
Okay.
Yeah.
Thank you.
Yeah. Okay. I guess we're done.
Hello everyone, it's Mikael Salari. I'm a PhD student at Mälardalen University of Sweden. I'm supervised by Dr. Enoiu, Dr. Afzal, and Dr. Secheleno. Today I'm gonna talk about one of our recent scientific contributions named Choosing a Test Automation Framework for Programmable Logic Controllers in CODESYS Development Environment. This scientific contribution was published in ICST conference in April. So first I will start by giving you some introductory information about software testing of PLC programs. So first of all, we know that test automation is the process of automating software testing tasks such as test script development, test execution, and requirements verification using automation test framework. Choosing the right test automation tool received significant attention from both academia and industry in recent years. Based on the claim that is mentioned in the second reference that we have in this paper, we know that selecting the right test automation tool is a non-trivial task for many practitioners. So motivating by actually addressing this problem for choosing the right test automation framework for practitioners, we developed 4 different research questions in this study. The first research question is that what are the reported test automation frameworks for CODESYS in the grade literature? The second question is that what are the reported features that should be considered when choosing a test automation framework for CODESYS? We also developed a question that mentions that how do different test automation frameworks for CODESYS compare in terms of different features? And finally, we want to investigate on this subject that how do different test automation frameworks for CODESYS compare in terms of their applicability to an industrial use case? So, first of all, why did we choose CODESYS as our focused integrated development environment for PLC programs? Why we didn't choose any other IDs? It is because of 3 main reasons. First of all, CODESYS is free to use for personal usages, and also it is very popular in industry. It is being used by a lot of automation companies across Sweden and other countries. Secondly, CODESYS is device manufacturer independent ID, so it can work with different actually brands of PLC devices, and it has simulators. And finally, actually, CODESYS supports all programming languages that are supported in IEC 61131-3 standard, including function block diagram, structured text, ladder diagram, IL, and SFC. In this figure, in this slide, you can see the interface of actually CODESYS ID and also an example as a PLC program that is developed actually with some function blocks. So in this slide, I want to talk about the methodology that we used in this paper to address this actually problem of choosing the right test automation framework in a systematic way. As you can see on the figure 2 in this slide, the process will start by number 1 when we apply the grade literature review to detect the test automation frameworks, the most discussed test automation frameworks of PLC devices in CODESYS ID. Then we use a literature review to extract the test automation framework features or TAF features that are more important from the academic point of view. Then, since we want to have an industrial validation on the detected features, we feed all of these academic reported features, test automation tools features, to an industrial company, and we ask the software engineers there to validate the test automation frameworks that are more important from their point of view. So after this industrial validation on the test automation frameworks, then we have the selection of the most important test automation frameworks, and based on this most important test automation frameworks, framework features that we detected, we have a comparative study based on the actually we apply it on the test automation frameworks that we found. And then we apply it on industrial case studies that are provided to us by a big automation company in Sweden. So we have a hybrid methodology because it will combine a GRE literature review and an industrial case study. You might ask why we use GRE literature review and what is GRE literature review. GRE literature review is like actually using a search engine to gather the information that we like by combining some search strings. But the reason behind this actually logic that we use GLR or GRE literature review is that first of all, GRE literature review will exclude all of the academic results. So it is just based on the practitioner's point of view, their discussions on the web forums, their discussions on different sources that are available on internet. And then also we should consider that the GRE literature review, that procedure that we use in this paper, it is inspired by guidelines used by Raulamo et al. In their paper, and they evaluated the efficiency of this methodology in their paper. Thirdly, GRE literature review will lead us to create a pool of objects, but the contents of this pool of objects need to be screened and analyzed based on some criteria. And finally, I should mention that the pool of the source that I mentioned is available online at GitHub, so it is open source and you can have access to it. So for performing GLR or GRE literature review, we need some search strings. And the search string that we used for this actually goal in this paper is as follows. You can see we combined these words as a search string, CODESYS, and also we have some synonyms like test, testing, automation, automated, automatic, framework, and framework with capital letter. After actually finding all of the results in the pool of the sources, then we need to somehow define some attributes to filter the results and divide them in different sections. To this end, we consider some object properties, as you can see in the table in the upper part of the slide. You can see every subject is actually divided by the title, link, extracted framework from that link, object type. It means that does it have documentation or not? Or I mean, is it a documentation, tutorial, description, a discussion between engineers or practitioners on a forum, or it is the other kind of the objects? Then we also made it clear that it is a literature type. I mean, it is a GRE literature review or it is a formal type. And also we have the demographic info, like the year and the author's organization and author's name. Then we need some selection criteria for GLR. For criteria, we consider the following actually criteria like author's credibility based on the Alexa rank of that link and also referral sites to that link. We also considered the CODESYS verified feature here. It means that we should see the tool that we extracted from that link using GRE literature review is validated or verified by CODESYS official website or not, or in their documentations or not. And the final actually thing that we considered here is the support feature of version 3 actually family of CODESYS, because it is the latest version of CODESYS and it supports a lot of test automation frameworks and a lot of add-ons. So we wanted the tool to be updated and have this compatibility with the latest version of CODESYS. Moreover, what we have in this next step of the methodology. In the methodology, we want to also, as I mentioned before, discover and validate the features of test automation frameworks and see which features we should consider in our comparative study between the discovered test automation frameworks. So to this end, we detected most important industry reported features while choosing a test automation frameworks based on 3 different sources of extraction. The first source that we use is the literature review based on 5 different academic papers. The second one is industry, which is the industrial automation company that collaborated with us in this research. and the software engineers there who expressed their opinion on the most important test automation features from their point of view based on the valuable experience that they have in this field. And finally, we consider the documentation of the tools as the source of extraction in this step. After discovering the features, all of these features fed to a company, a test automation company in Sweden, and we asked the software engineers there to evaluate the validity of these features. And later I will talk about the validated features in this presentation. About the industrial case study that we used in this paper, also I should mention that to evaluate the applicability of the discovered test automation frameworks for CODESYS, in a real-world scenario, we used an exploratory case study using an industrial system. The case study, as I mentioned, it's provided to us by a big automation company in Sweden. And let's talk about the results that we achieved after applying all of these methodologies, and also I will talk about test automation features that we could extract. So as you can see, based on the results that we could conclude and we could gather in our methodology, we found that the most discussed test automation frameworks for CODESYS are CODESYS Test Manager and also CO Unit, which is formerly known as CF Unit. CODESYS Test Manager, I should actually mention that is the official test manager or test automation framework that is provided by the manufacturer of CODESYS, and it needs license to use, so it's not free to use. But CO Unit, the second one that is the most discussed test automation framework in this regard, is free to use. It is open source, but it has a lot of limitation in its use, and I will discuss it later. So, based on the three sources of information, including the academic related works that we mentioned here, industrial input, and official documentation, we discovered 29 industry reported essential features. 15 out of these 29 discovered features were considered important by a group of software engineers in a big automation company of Sweden. Here we can see the results in two tables. In table 4, on the upper part of the screen, you can see the extracted and validated framework features that actually considered as important by industry. And in the second one, you can see the other extracted framework features that were extracted from academic sources, but from the industrial point of view, from the point of view of engineers in that big automation company of Sweden, they were not important. So as you can see in this table, all of the actually features that we extracted are divided in 5 different sections, including company constraints, such as cost and supported platforms, maturity, industrial usage or stage of development are the heads here. The next category is testing functionalities, such as playback record, test suite support feature, and test suite extension feature. The next category is tool flexibility, such as teamwork support, and the final category is usability, which is pointing out at a script language that the test automation frameworks will support, continuous integration support, and etc. The next result that we found, and it was regarding the research question 3 that we had in this paper, is mentioning that based on the 15 industry validated features, the results show that CODESYS Test Manager on average is more mature and has several advantages over CO Unit, which is the open source counterpart here. And this maturity features that we are mentioning are like some things like user support, record and playback features, and easy test suite extension. However, we should still mention that CO Unit as an open source counterpart also provides testers with many key features, and we cannot judge this tool as a bad tool. It's still good and it's useful for the practitioners' needs to some extent, but of course it's not as mature and as good and well supported as CODESYS Test Manager. Here we can see the results of the comparative study based on the just industry validated test automation features that we received from industry. You can see, for example, in the green column, we have the test manager features, and in the actually yellow one, we have the CO unit features. You can see, for example, in terms of cost, test manager actually needs commercial license, but it is free for academic license, academic purposes, and we used also this academic license. CO unit, but on the other hand, it is free and it is it has the open source license. From the stage of development point of view, we can see Test Manager is more mature, 8 versions released so far, but CODESYS is, CO unit is just developed through 3 different versions. Test Manager supports playback record, and also it supports test suite support. On the other hand, CO unit doesn't support playback record, and also from the test suite support point of view, it just supports .xml actually extensions in this regard. Regarding the script languages that are supported in these 2 test automation framework, which is a very important feature, we can see that Test Manager supports all IEC 61131-3 supported languages, such as FBD structures, text, ladder, and etc. But CO unit only actually works based on the structured text programming languages. If you are interested in more details of this table and this comparison, you can also take a look at the paper that we submitted and published regarding these actually tools. And if I want to also talk about the results that we gathered regarding research question 4, I should say that we used some kind of industrial cases studies in this paper, and we applied both of the Discover test automation tools on these industrial case studies. I should mention that this industrial case study that we use is part of a supervision program of cranes, and it is developed through different POUs that are developed in 2 different programming languages, including function block diagram and structure test, and they work in collaboration with each other. So for actually this industrial case study, we applied both of these test automation tools to evaluate their efficiency and to see if they are actually in alignment with the results that we gathered using our methodology. Are they good enough as they claim in their specifications and documentations or not? So we had 2 different test execution scenarios in actually our result section when we wanted to evaluate that case study. And for each tool, we developed 10 unit test cases. So it was interesting because after applying these tools on this case study, we could also identify some new features that are somehow ignored by both industrial actually evaluation and also the academic papers that we analyzed in this paper. One of them is installation and configuration, which is mentioning that if these tools are easy to install and configure for users, ease of use is another feature that we discovered. Testable objects is also another very important feature that we didn't see in any of the actually source of extraction of features. And it means that, you know, we have different objects in CODESYS in a PLC program. It can be the network, it can be the POUs, or it can be the main program. For example, in CODESYS Test Manager, you can test everything. Basically, you can test the network between the different POUs. You can test the POU directly, and also you can test the PRG. You can alter everything. You can automate even the logging inside the PLC devices, simulator, and everything. But in CO unit, you can just actually test the main program. And the other thing is that for CO unit, which is actually observable in figure 3 and figure 5, everything should be, you don't have a user interface and you should develop everything in text, in structured text language. And for each instance of, for each test case that you develop, you should instantiate all of the actually program, POU variables and everything again and again in the main program, in the test case, So it's very time consuming if the size of the program becomes bigger and you need, in cases that you have actually a large number of test cases, you have a lot of difficulty to instantiate them again and again. But with CODESYS Test Manager, you don't have this problem because you can easily modify the inputs on the POU as well. And test assertion timeout is another important feature that we discovered here. It means that in actually CO unit, for example, you cannot dedicate some kind of time budget for test assertion like a timeout, but in actually CODESYS Test Manager, you can modify it, and I think it is also a valuable feature. And finally, regarding the research question 4, the final research question, which was about applicability in an industrial case actually study, we can say that the comparison based on the detected features can make us actually confident that regarding the installation and configuration, also CODESYS is the winner. Because of the reasons that I mentioned in the last slide, ease of use and testable objects, and also test assertion timeouts are the other actually very valuable features that are supported in test automation in the test manager. In figure 4, you can see a picture of actually a screenshot of CODESYS Test Manager. You can see that you have the very high level of readability. You can you have some test actions, and I think you have something around at least 50 different test actions. And by these test actions, you can easily automate the things that you want to do in the CODESYS. You can log in into PLC device, you can execute programs, you can alter the inputs, you can have different exceptions, like some kind of errors as expected output, or you can have the actually expected output as a actually number. So it has a very good flexibility in terms of actually testing the program. So about the conclusions, I just want to mention that this paper, as I mentioned, addressed the practical problem of choosing the right test automation tool of PLC programming CODESYS ID, and it helped one of our actually industrial collaborators in VeriDevOps to know which test automation tools, because of the reasons that we actually justified in this paper, is better for them to use. And also it helped us to use the right test automation tools in our actually upcoming scientific publication when we want to transform a PLC program to Python code, and also generate and execute some test cases in both Python IDs and CODESYS ID. And now in that paper, we also use the results of this paper, and we know for CODESYS ID part, we should use Test Manager because of these numerous features and advantages. So in future research, we plan to conduct a more comprehensive evaluation of CODESYS Test Manager in another publication, if it is possible, when it's used in an industrial context. And also we want to investigate how to connect such a test automation framework for automated testing of timer and stateful function blocks that are usually very challenging for the researchers because of their actually very unique structure. So we have some references that I talked about in this paper and also this presentation. And thank you very much for your time. I'm available for any questions.
How long take you to produce the test that you mentioned? You say that there are 29 features And did you obtain 15 tests or something similar?
How much time we used for it?
Yeah, how much? How long?
Actually, we didn't measure the time that we spent to gather the results, but the thing is that different factors affected this time. One of them was the time that we were waiting for the industrial engineers to reply to us. And the other one was when we wanted to also extract the features and evaluate their efficiency based on the academic papers. So I cannot give you the exact time that he spent on it because we didn't measure it. But overall, I can say that it's not a very long process because it is somehow systematic. And from the actually also this point of view that these features actually do not cover all the things that might be important. You can see that we also discovered some new features during the test, during the industrial case system. So yeah, that was the actually all information that I had in this regard.
Yeah, but you have how many? 3 months, 4 months?
Approximately, this paper took something around 4 months of my time in overall with great literature review, filtering, screening, having the literature review, having the feedback from industry, case study. For me, it took almost 4 months.
Yeah, did you compare with classical test methods like model-based testing?
It was this research. It was more practitioner oriented. So and this is why we use great literature review, because we wanted to know the opinion of practitioners and software engineers. And in great literature review, in the first part, we don't include any academic results because we wanted to understand what is their needs exactly. And this is why you can see we had 29 features discovered by academic papers, and they were reported as the industrial features that are important for industry. But when we feed these 29 features to actually industry, they say that just 15 of them are important for us. So maybe always we don't see the clear reflect of the opinion of industry and practitioners in academia.
Test automation execution, more like on that side than more.
Yeah, it's more about just the test automation of the execution. We don't care about the test generation or whatever in this paper. So.
Okay, thank you.
Thank you for your question.
Thank you. C'est pas moi.
Thank you. Now we will have a short break and we come back at 11:30.
Hello. I will start the first presentation in this session. So my name is Wissam Mallouli. I'm working for Montimage company. Montimage is a French SME expert in security monitoring in general. And I'll present the work that has been done in the context of a VeriDevOps project, where we adapted and used our monitoring solution in the context of one of the case studies provided by EBB, a load position system. I will present this case study later, but first of all, sorry, so we had a small issue. Do you hear me again? I hope so. So I was saying that we applied this monitoring solution to a load position system case study provided by EBB. I will present some experimentation, some results. We started with some safety properties, so that this will be the main topic presented in this presentation, but we are continuing this work for more security properties. So
you are again muted, Wissam.
do you hear me?
Now, yes.
I don't know why there is a small problem. Yeah, sorry again. So we have this question related to which are your cybersecurity related challenges. So we asked this question to 337 participants, and we get 758 answers. And as you can see, that the majority of them say that they are really afraid about the injury or death of their employees. So cybersecurity is really, really very impactful, and this is important that we care about it. And of course, if you see the three other answers that have 28%, so damage to product service quality or loss of proprietary or confidential information, or cost of incident response and mitigation. So all these challenges are really very important, and that's why we need to take care about cybersecurity. Of course, we do it during development. We are doing in general risk analysis, but even if we do this work at the development phase, still some vulnerabilities and some risk are can be available during operation. That's why we need to monitor during operation. We need to detect these issues, and we need to react. These issues can even be new vulnerabilities that are coming after the deployment of the system, and we need to take care about these new vulnerabilities, because if we say that there is a new vulnerability, that means that some new attacks can exploit them. Let's see the basics of this, let's say, the terminology. So a vulnerability is a weakness that can be exploited by criminal. So in general, we are always investigating if there is new vulnerabilities on the system that we are using. And of course, we are
always discovering new vulnerabilities, and there is always new exploits of these vulnerabilities that are coming. So finally, we are in front of cyber attacks that can be either known attacks, because we know already how they are working, but we can also be in front of new cyber attacks, and we don't know actually their signatures, and that's what this makes the monitoring in general difficult. That's why in general in intrusion detection systems we have two main approaches: the signature-based detection, where we recognize some bad patterns that are known. So we have these fingerprint of these attacks. So we'll only write in general some detection rules that will allow to check if these attacks are available on our industrial system. And of course, if the attack is not known, in general, we rely on anomaly-based detection. And in this case, we rely on machine learning and AI techniques to detect deviation from a model of good behavior of the system. And these are, in general, the two main approaches that we can have for intrusion detection system. Of course, both of them have pros and cons. Signature-based detection is, in general, very easy to implement. We have, in general, a database that will integrate the known attacks that we want to detect. But of course, the challenges is to choose the techniques and algorithms to accurately and efficiently detect malicious behavior and intrusion, and also identify the signatures of these attacks. And sometimes attackers are doing some small mutations of their attack, and in this case, the signature can miss these specific attacks. For machine learning techniques, of course, the idea is to apply these algorithms to learn from normal behavior and detect all the deviation. This is something in general time consuming, and even the detection in general can provide several false positives, and there is a lot of challenges to apply this kind of methodologies. The first challenges is to have data sets. It's not easy to have good quality data sets, either for the normal behavior or the abnormal behavior. And of course, there is all the possible, let's say, AI-based attacks that can be applicable during the training phase, where we can provide some, let's say, malicious data sets to finally to build a wrong model of a normal behavior, or it can be also applicable during the test phase of machine learning techniques, where we can have this adversarial machine learning techniques. So we try to implement all these approaches in a unique tool that integrates these different methodologies. So the first challenge is, first of all, to parse different kind of logs from industrial systems. So we build a first module for feature extraction that have a plugin architecture, allowing to handle different communication protocols, but also different structures and structured data. The main idea of this feature structure is to normalize the information that can come in these logs. And these logs, of course, can be either pre-captured logs in the format of files, or can be also provided in a streaming mode. And after this feature extraction, we can either apply rule-based monitoring techniques, so based on classical, let's say, rule detection, or we can apply some machine learning techniques to perform anomaly detection. And we added within these two modules another module that is related to the identification of the origins of attacks. because sometimes when we have an alert that is provided by, let's say, an ML AI-based detection, we know that there is an anomaly, but we don't know the origin. So we need to investigate more and to be able to, let's say, automate as much as possible this investigation. We build this root cause analysis solution that help operator to determine the origins of attack to finally select the best countermeasure that can be applied in a specific context. So all these modules has been implemented and provided as an open source solution that you can find on GitHub. If you go to the Montimage GitHub, so github.com/Montimage, you can find these tools that are available for the community and that can be easily extended either to parse new type of logs or to add new detection rules or to apply new machine learning techniques on your solution. So we wanted to apply this solution in one of the case studies of VeriDevOps project, this load position system proposed by ABB. So where we have some camera in the crane that allow to capture images of moving load. The camera in general perform a local analysis of the picture to be able to provide an array of coordinates of what we call camera markers. And we need to check if these are real markers or not. Because we can have some reflection on the sea in a port, for example, or so it can be mistaken. And the idea is that we wanted to apply our methodology to check if there is some abnormal markers or not, and we to compare it as a reference with the PLC solution. So our, let's say, Oracle is the PLC result. First of all, we try to apply some rule-based analysis of these markers. So we try to have some rules related to the number of marker candidates, to have a threshold for this number, to also work on the speed variation of these marker, also their displacement magnitude, etc. I will not show you the rules that we build because it's somehow confidential, but at least when we apply these rules and also combined their results, we had an accuracy of only 73%. This is something normal because there is no real rule on that can give a specific threshold either on the speed or on the displacement magnitude or whatever. We are in the context of this case study where we don't have any signature of bad behavior. That's why applying machine learning techniques is better. We, in fact, tried different solutions to make some clustering, some auto encoder solution, and we had some, let's say, better result. But in fact, when we applied a multi-layer perceptron classifier with a specific with two hidden layer with 4 neurons with some specific, let's say, configuration, we were able to achieve an accuracy of 99%. Of course, if you are dealing with the same crane that have the same configuration, of course, because in some cases we can have different configuration of cranes, and of course the data sets that we are using for learning can build a wrong model, and in this case the accuracy is not let's say good enough. Let's say this work allowed us to make a publication in a conference, but we are still progressing on this work to focus on more security scenarios, how we can remotely control crane and how an attacker can benefit from this remote communication to perform several kind of attacks. So we are working on this today. We are also integrating this automation of root cause analysis to determine the origin of incidents. To better select the countermeasures, the idea is also to automate as much as possible countermeasures, and we started performing this first state of the art of possible countermeasures during development and during operation, and we'll continue this good work in the context of VeriDevOps. This is what I have for this presentation, with some good references and also some good publications. If you have any question, do not hesitate to ask. If no question, we'll move to the next presentation. Yeah.
Slide you mentioned identify new attacks.
It's not new attacks. It's the idea. We are working on some safety properties. Not
Yes.
Yeah. For this experiment. Now we are moving to some other scenarios that will involve some security properties. And this scenario is related to the remote control of cranes. Okay, so there is some operators that will provide some request to the crane to do some specific tasks, and the idea is that an attacker can try to be man in the middle, for example, perform some man in the middle attack, or even can have some even internal attackers from the real, let's say, secure network. The idea is also to check if there is some misbehavior, let's say, some security issues, but also some tasks that cannot fit together. Let's say that I'm taking a load and then directly I'm how we call that, dropping it, and this is something that should not happen at all. So all this kind of thing can be somehow specified, and we can specify also some signature-based attack detection and also some ML-based detection on that.
Category of an attack that you already know.
Yes.
But it's a behavior that gets into that attack.
Yeah. The tricky thing in this experiment is that all the traffic is encrypted. And in this case, we are obliged to use some machine learning techniques to, first of all, classify what kind of activities we are doing, and then later, of course, to correlate these activities and check if there is any issue. But other work are also under investigation in this area. Thank you a lot.
Okay, so just to make sure that everyone can hear me, no? Yes? Hello? Okay, so my name is Tanwir. I will present an approach where we use deep learning to detect for the early detection of network attack. So I'm from Akademi. So the overall idea of the approach is this, that you have a system that you would like to protect from the network attack, and we have the early monitoring tool, which is observing the traffic between the system and the public or untrusted network. And you have some set of models which are trained to detect certain set of attacks. And based on the traffic, we use this network to kind of generate a prediction that either this flow or the network flow is going to be malicious or not. And then based on this prediction, and we try to predict as early as possible. So we do not wait for the attack that we have the complete information about the communication session or the entire traffic for the attack. We try to detect as early as possible, and then so we can deploy some countermeasure to kind of reduce the damages that the attack can do. So this is the overall idea. And in this project, we would try to implement this on our case study provider on Fagor and ABB. In case of Fagor, we have trained a model to kind of detect attack from the Where is the full screen? Okay. So in Fagor, they have two network kind of interfaces. So they have this web application, which has REST interface, and we have trained a model to kind of detect a web-based attack. And then they have MQTT infrastructure where they use detect. They have different sensors which send MQTT protocol to send information. So we have a network. We have trained a network which can detect MQTT based attack, and we are also planning to use our tool in ABB case study where they have some internal network communication where we can use our tool to kind of detect different attacks. So overall, our approach has two main steps. The first one is training, where we train a machine learning based model to detect attack from different application domain. We are using some public data set that are available, and they have a normal traffic, and then they have traffic when they conducted different non-attack to our application. And once we have trained the model, then we can plug it in our tool that uses that model to kind of detect ongoing attack. Just to kind of give a little bit of introduction, I think Wissam, in the previous presentation already gave some idea that what is intrusion detection basically. So this is just these are the systems that are kind of observing the network traffic, and their job is to kind of detect attacks and then report them to our administrator so the administrator can take some action. And in most cases, these network intrusion detection system, they are categorizing or grouping packets in flows, and flows are based on a network flow kind of represent a one communication session between two network endpoints, and they are grouped based on the source and destination addresses, ports, and the protocol type. So basically, in this down here, we can see that there are some packets that going from network to system and then from system to network, but they are kind of grouped based. If we can kind of group them, they are like two flows. So the blue packets belong to one flow, and then the green one belongs to other flow. And we kind of do prediction. We can do prediction per packet also, but it's if the application the communication session is so each packet is not carrying independent information, and they are related to the other. So it's better that we do it per flow than per packet. And most of the traditional intrusion detection system, basically they use statistical feature, which they extract from a flow. Basically that first they collect, wait for the entire flow to be completed, and then they extract different kind of statistic, like how many number of bytes were sent forward, how many bytes were received backward, packet count, what was the IP address and the port number. So this kind of feature that they use, and then they try to classify the flow based on those feature. But the problem with these approaches is that we in order to collect this kind of statistical feature, we need the flow to be completed. So we have the whole information. And only then we can extract this feature or the meaningful feature out of them. But this means that the attack has already been executed on the system and it has caused the damage, which is it might not be very ideal. So the idea is here in our approach is that we want to detect as early as possible. So we try to utilize the information that is available at the moment, and then we kind of tell, okay, it's most likely to be an attack, and then we can stop before the attack is completed. And in the training process, as I mentioned before, that we use some public data set. For example, to train a model for web application related attack, we use this CIC IDS 2017, and then for MQTT we use this MQTT IDS 2020, and these are public data set, and they have traffic for different category. They have traffic where they doing normal activities, and then when they have traffic when they were conducting some attack. So once we have the model, the monitoring process looks something like this, that as soon as we get a packet on the traffic channel, we put it in a flow, and then we provide that flow to a classifier, and then classifier can say, okay, this looks like a normal traffic with this confidence. And then as soon as we get another packet for this flow, we provide that flow again to our classifier. And now, since classifier has more information, it says, okay, this looks like an attack, but the confidence is a bit low. So as soon as it gets a third packet, so now it has more information. Now the classifier is quite certain that this is looks like an attack. And then at this point, we can either alert administrator, or we could do some countermeasure by blacklisting the IP address or something like this. And in real environment, you don't usually have one flow because there are many services. There can be many clients that are using your services. So you have several flow in parallel. And then as soon as any flow is updated with a new packet, we use a classifier, and then we will get this kind of prediction, like based on the classifier that, for example, here we say that if we have 3 classes that we have trained our model to detect attack type 1 and attack type 2, then you will get this kind of output that for each flow, like what are what model thinks basically. So basically, for example, for flow 1, the model thinks has a 60% chances that this is a normal, and in case of flow 2, the model is quite certain that it is a attack type 1. And then you can also modify the classification threshold to kind of control the false positive rate. So evaluation, we use as I mentioned, this CIDS 2017 dataset. We use the flow in these with these classes. So we have quite a large number of flows for normal class, and then the length is like the number of packet in a flow. Was on average was 124, and then we have different attack, brute force, cross-site scripting, and then SQL injection. And these are their flow length. And from a classification point of view, we achieved a very good performance. Obviously, our classifier did very well for normal class because we had a lot of data. And then for the brute force attack, it was quite good, the precision and recall. And then it did very well for SQL injection attack because there were only 21 sample, and then we use 70% of this data to kind of do the training, and we use 30% for the evaluation. So we ended up very few numbers for SQL injection to kind of to train our model. So this was from a classification, and then to assess the earliness, that how early that we can detect an attack, we define a new metric, earliness, which using this metric, if the value of this metric goes from 0 to 1, and if it's 1, it means that the classification, so our tool is able to kind of predict the correct class of a flow by looking at only one packet. And if it's 0, it means that the model required all the packets in a flow to kind of correctly predict the class. And so this is the earliness for our classes. So for normal class, on average, we could correctly predict the class of the flow by just looking at the first 2 packets. And then in case of brute force and cross-site scripting, by looking at only the first packet, and then in the SQL injection, by looking at only first 2-3 packets out of 5 and 11 and 18. So, and then we use another data set with, as I said, that for MQTT to kind of detect MQTT related attack. And it has a different kind of traffic related to different attack, and these were the number of flow that we had in different classes. We have a large number of packets for brute force. We have and then in this case, we have very few sample for this scan SU attack. And so basically, the result was quite, I would say, more or less predictable in the sense that the model did quite well for those classes which have more sample, and then did not do very well where the number of sample was low. This is a common problem with all machine learning algorithms and approaches. And in terms of earliness, we got a quite good result in the sense that we can tell with the exception of Sparta, we could correctly identify the class by looking at just first or second packet. But in case of Sparta, we need to look at least first five packets to kind of correctly predict the class. But if you look at it, that it was on average length was of for Sparta attack, it's 20, and then we only require 5 to correctly predict the class. So now let's do demo. So the tool is open source and it's available in VeriDevOps GitHub repository. It has two. It's not visible. Oh yeah. Yes. So it has two component. Basically, it has early display. So basically, it just listen for it just display information basically. And then the main component of the tool is this monitor, which observe the traffic and makes a prediction. And then it has a REST interface where you can the tool or script can query the REST interface to kind of get the results. And the input for this tool can be, we can also specify the interface, live interface of the machine, so it can observe the live traffic. Or you could also provide the recorded traffic in form of a PCAP file. So here I have a PCAP file, which I would like to monitor, and then first we run the display. And then we run the monitor. Takes a while. Yes, so it has 5 flow. The first one is the normal. So you can see it's, and then it also tells the number, the length. And you can see it here that it was changing the, as it gets more information, it might change its prediction and at the confidence level. So this was the cross-site scripting attack, and then the second flow is representing a brute force attack. And then we have a third flow, which represent SQL injection. But the idea is here that you can see that it's as we get more information, the prediction becomes more like it becomes more correct, or it has more confidence. But then again, it's a trade-off that either we wait for the attack to be completed, or we kind of deploy some countermeasure, and then later we could see if it was the correct decision or not. So this was the demo. I think I have a few more slides. So we have the tool support for this our approach, where one can have several models that are trained to detect different attack, and they can be reused. As I mentioned, that we can also monitor traffic or attack in real time by sniffing the interface, network interface. We can also build a script that are ingesting the information or polling the early monitor tool to kind of see what is the prediction, and then they can do different action. And this is to kind of help administrator to kind of automate some of the preventive measure in a timely manner. So in conclusion, we have published the result and we have published our paper, and basically in the paper we propose a CNN-based classifier. You can find more information there, and the new metric that I discussed, and the evaluation we done using 2 data set, and then how we can accurately predict the network attack by looking at only first 2 packets. Thank you very much. If there are any questions. So, is there any question in the chat or something? Yes, please.
So can you go back to slide 19?
Oh, 19.
Yeah, I guess it relates to numbers. 19, yeah. No?
We have 17 and
No, this one. Yeah, the next one.
This one.
No, yeah, this one. The number of flows. So just to understand, it's like for average flow length, so how many execution, or how, because this is the average flow length. So how many, what was the distribution of the data? Because I mean,
so
if this was the average, what was the standard, if you measure standard deviation or
something? So we measure the standard deviation, but now I don't think so. We reported in the paper. I have it here.
Okay, no, I'm thinking is that, of course, that influences, I guess. Well, why is that? Well, you have a big difference between
the number of samples.
Yeah.
Yes. So
why not?
So this average flow length is this is calculated only within this class. So it's not like across the class. So so you're saying that it might be so that you have few samples that this is kind of, yeah. I think this is a.
Then the comparison is not.
It's a valid concern, but it's a problem that with this imbalanced data set. We also discussed this in the paper that we had to use this this class weight that we kind of, when we are training the model, that we kind of punishing the model if it if it makes a misclassification error on the class where we have less sample kind of. So yeah, it's a problem when you have a hugely imbalanced data set.
Yeah.
But what we tried here, that we also discussed in the paper, that when we are doing the evaluation, then we need to be very careful when we have imbalanced data set, that we do not. So for example, it has been suggested that when we have an imbalanced data set, you should not use accuracy. You should use balanced accuracy. That accuracy can, if you use accuracy on an imbalanced data set, it can give you like a false optimistic result. That is, you perform very well, but in reality it's not, because it was imbalanced. And then here I also didn't talk about this book marker something informedness metric, that in the literature is suggested that you should use this metric when you have huge imbalance in the class to kind of get better evaluation than I think it's called bookmaker informedness, and it's the probability that tells that the classifier, when the classifier making a decision, whether it was just completely random guess or did it actually learn something. So as the value approaches to 0, it suggests that just classify just making a random choices. It's not learning anything.
Thanks.
Yeah. Okay. Thank you very much.
It's not share this. Okay. I thought it was already sharing. So yes, I think it's. I prefer to share the screen. Everything okay? Yes. Okay. Well, hello everyone. My name is Angel. I'm from IKERLAN, and I finished my PhD thesis a month ago, and now I'm going to present a little bit the tool that we are developing in IKERLAN to track the vulnerabilities of a given system. So first, I'm going to give a little bit of the context and how the initial idea was made, and then I'm going to explain a little bit how this tool can be used and maybe a little bit about the architecture. But because I'm the last one here doing the presentation, I do my best to keep this as fast and painless as possible. So let's start. First, the context here, I think it's very, very easy to understand because in general, industrial systems are not outdated regularly. So this made them prone to vulnerabilities along all their life cycle. Moreover, in this context, when they are developed, both hardware and software pieces and elements are being recycled and reused, for example, from open source or components of the shelf that can be, in most cases, directly integrated into the development. This make them more more cheap to develop, but also this feature make them prone to more vulnerabilities. And finally, because they are getting more and more complex over time, because of the more features they have and the more elements from different sources that we're integrating in our development. So tracking all the vulnerabilities here and updates, it's very difficult. So in general, this scenario make industrial system very prone to vulnerabilities. In fact, this is shown in the data because public non-vulnerability databases nowadays have over 150,000 entries. In fact, in the year 2021, almost 22,000 vulnerabilities, new vulnerabilities, were added to these databases. So with this in mind, and with the aim of including all the existing standards that can help us to track these vulnerabilities, we also wanted to include, I don't know if I can active the pointer here. We also wanted to include the more relevant standards in this path. So, for example, here the CPE standard helps us to identify in a unique way the system that we want to analyze. Here you can have an example of what a CPE string would look like. So here we are identifying Internet Explorer version 8.0, the beta version, and in this case, the vendor is Microsoft. Another standard that we can integrate here to help us identify the vulnerabilities that we want to track is the CVE standard. In this case, this standard, instead of identifying a system, an asset, a platform, or an operating system, here we use this to identify vulnerabilities. So this standard assigns a unique identifier to each vulnerability that are discovered every year. And finally, even though we have a bunch of standards that we can integrate here, we think that the most interesting one in this case is the CVSS, that for each vulnerability assigns a severity value proportional to the severity of a vulnerability. So it's a number between 0 and 10, and the higher the number, the more critical the vulnerability is. In this case, for example, this vulnerability shown here with the CVE has an associated value of 7.4 that corresponds with a high in the nominal scale of the CVSS. The other two standards, even though they are very important, they are not directly integrated in this tool. Then, using the previous standards, the main idea here would be to be able to track the vulnerabilities of any software application, an operating system, or a hardware platform. Taking this information into our tool, it would be desirable that we can apply this tool, as I said before, to software, hardware, and industrial control systems. And it's important to notice that we want to track publicly known vulnerabilities, okay? And this tool would work both locally and from the cloud. And finally, the result that we ideally want to obtain would be the list of the vulnerabilities associated to the systems that we are analyzing and the degree of criticality of each one. Then with this information, of course, we could extract some conclusions as which vulnerabilities should we patch first, and ideas in that way. So with this in mind, the main point here, and this is because of how the standards are made, we want to differentiate two main elements to track, okay? We named asset to the whole system, and each element that we can extract from that asset, we name it component. So an asset, as I said, would be the whole system that we want to track, and each component would be every individual pieces that we can find in the vulnerability databases. So here, the main functioning of this would be a database inventory that would have all the assets that are present in the vulnerability databases, the vulnerabilities that can be found in those databases. And I think that here a very important remark is that we don't only want to analyze one source of vulnerabilities. We want to integrate information and gather all the information that we can obtain from more than one vulnerability databases. And finally, with the information of the assets that we have available and their vulnerabilities, we want to implement a task planner so we can make a request to the vulnerabilities databases, and every time a new vulnerability is discovered, we can update the information of our system. Here, you can see a little bit a summary of the life cycle of these, in general, of an industrial system. And I think that it's very important that we can start applying this tool from the very beginning of the life cycle, because from the design, we can know which asset we would like to track when this device is deployed. In the implementation, maybe we know almost exactly what kind of assets and components we want to track, and with the definition of those components, we can load the information to the system, to the tool, in this case, to TOEI, and every time a vulnerability is discovered, we can create an alert so we know that a change has been made to the system. And this means also that we can use this alert to patch existing elements and existing systems in the wild. Here you can see maybe more detailed architecture of this tool of TOEI, and I think that the very important pieces of this tool would be, first, the threat finder subsystems. This subsystem is in charge of gathering all the information from all the different databases that we have available. Here, we also want to standardize all the information that we gather, because every database represents and stores the information in a different way. So here we would like not also gather that information, but also we want to standardize its representation. In this case, for example, using a structured JSON file with the common fields that we want to store in our databases. The next important point here would be the database itself that has the information about in this case, the component that we want, that we can track, and also the vulnerabilities associated to those components. Then the scheduled subsystem that, as I said before, is in charge of knowing which elements we want to track. So here we have this configuration database that has all the information about which component we are interested to track over time. Here we can configure also the period of time when we want this updated to be performed. And finally, I think the last bit of this architecture is the interface. In this case, we have two kinds of interfaces, an authenticated and the other one is an unauthenticated interface. One is for the public, in general, for the public queries that the users can be made to this tool, and the other one is an authenticated interface for the internal uses of an organization, because we don't want someone from the outside to know what kind of tracking are we doing internally. Here, as you can see, I take some screenshots of the tool of Zoe, and here you can see the main dashboard where we have here the total assets. Remember that assets represent the systems that we are tracking and all the components associated to those assets. Here you can see also the total number of vulnerabilities for all the assets that we are tracking. Here, for example, you have the list of all the assets that we are tracking, the components that each asset has associated, and the vulnerabilities associated to each one of those components. Here is a more detailed vision of a component in this case, and you can see all the vulnerabilities that has associated. In this case, here at the bottom, you could see all the list of the vulnerabilities for that component and a little summary of all the details about this vulnerability. This finally would be all the list of components that are available to include to the track. As you can see here, you can see the reference of the CPE identification from each one. And of course, here you can add your own, but a search for the specific one you want to track. And yeah, almost for finishing, in summary, this tool, Zoe, let us make an automatic surveillance of the system for vulnerabilities. And it's important to note that these vulnerabilities are known vulnerabilities. And we are able, in this case, to gather information not only from one, but from all the more, not all maybe, but from the most part of the available databases that are publicly. Then we also can integrate reference standards in this context, such as the CPE and the CVE that are really supported in the nowadays industry. And finally, it's remarks to say that this tool don't need to be running locally in the system that we want to analyze. So it's a non-invasive tool. And with everything in mind, I think that this is all for my presentation. I try to keep it as short and simple as possible. And if you have any question, you can contact me by email, or you can ask me now. Yes.
Have you run Zoe on Zoe?
I think that's a very good question. Maybe I'm not really sure about that. I don't think so. I don't think so. Yes. Yes. Could be, yes, integrating the databases now. But the
That was more I was thinking like our databases containing vulnerabilities, and then you want your own database there where you keep track of things that you want to track of.
Yes.
That doesn't sound like a unique idea. Are there other similar concepts out there, and why does, in what way does SOA differ?
I would say that the main characteristic in this case is using more than one database, because usually if a system like this is found in the literature, it would only use the NVD database. In this case, we know that more than one database of public available vulnerabilities exist, and I think that's the first differentiate fact of this tool. The other one I think is the tracking over time. For example, in my PhD thesis, it's true that I couldn't find, as long as I review the literature, a tool that integrates the component over time. So usually this kind of analysis is performed once, and then it's not updated. It's like we are going to perform this here, and the systems that are in the wild are not considered because they stay like from that last point of analysis. I don't know if I explain myself.
That's pretty much immature to the market. It's like releasing antivirus program for Windows 3.1, and that was the one that was like, these are the viruses right now that we know about, and it was never updated. So of course it was useless the same day it was released. So in a way, it's interesting that I mean, it's obvious that you will find vulnerabilities and stuff, not just on this day, on what that day.
Yes.
So maybe that reflects how mature the security market actually is. No.
Maybe,
Right?
yes. Any other question? I don't know.
Maybe a stupid question. How easy is to add a new data source?
How easy it is. I'm not that aware of that fact, because I think that right now all the tests that we've done are were made only with the NVD database. That is the one that we're using for our test, but I think it should be not fairly simple, but at least very simple at the end. Because yes.
So we decided modularly.
Yeah.
So we have to implement a tracker for each data. We have to normalize that data to store in to collect in a database. So for each new source, a new tracker or a new module is it's modular. So then it's a scheduler. You can configure it to. You can set which of the modules which of the sources you can use. But an item for each of the sources needs to be implemented. Yeah, data formats are not the same, so we have to normalize it to the story. I know, difficult to understand.
You studied who are the biggest contributors to databases?
What do you mean? Sorry.
The vulnerability databases. I know this is maybe not exact our field, but still, who are the biggest contributors? I mean, I have never contributed in such database.
Usually Windows.
So Microsoft then. It's Microsoft.
Microsoft will be one of the principal cons. After the patches, its vulnerability problems.
Yes.
I mean, at least with the one, the NVD, it's NIST. They are researching.
And when with contributor, I think he's not referring to maintainers, but
I'm
contributor.
thinking adding stuff to the database. That's a contribution.
So who's adding those? I'm pretty sure it's someone else NIST.
Yes,
Yeah.
yes, you have to make a request.
That's inside, no, this is.
Yeah, because it said 15,000 new threads are
Yes.
stored, so we can all 15,000 threads.
In this case, vendors are the ones in charge of updating these databases, and then they have to make a request to the NVD databases to add those vulnerabilities. But usually vendors or even in general, any researcher that is in that field, because it's very usual that a researcher finds a vulnerability in a system, talks with the vendor to communicate that it has a vulnerability, and then with the negotiation, they agree whether to talk directly with the NVD in this case, or first generate a patch and then public the vulnerability. So it's like some parts implicated, not just the NVD in this case. Yes. Yes.
Windows. This. Mostly hunters who are have a copy.
One thing that I realize now is like, those are US based, yeah?
Yes.
Are there any European ones that have sense? Because I think US centric ones give you ones that are important. No, there are things that carry the other, non-US countries.
I'm not aware of that. I think that even the NVD database, even though it's a US-based one, is very extended. Is commonly used everywhere. I think yes. I don't know. Yes. Any other question?
Thank you. Angel, thank you. So we are ready for this like finishing remarks. So in case audience you have questions, please let us know. You can raise your hand or anything. It was actually was very nice to see all of you coming. I hope it was very useful to use, but still tuned. Stay tuned. Also, we recorded all the presentations, including one of like 2 in the morning, 3 in the morning. So there will be more presentations. Also, we'll distribute some notes about the meeting. So please subscribe to our channel, make like, okay, on YouTube. See us also in LinkedIn, and we will run this type of workshops once again in a couple of months because we really want to share with you and give you your feedback about what we do in our project. So with that, if there is no further remarks, so I thank all the participants and contributors to this workshop, all the organizers who made this whole thing possible. Thanks IKERLAN for hosting us here in the very nice laboratory. And see you next time. Bye-bye, everyone. See you.
Bye. Bye-bye. Thank you. See you.
Bye.
Bye-bye.